Welcome back. So, here we will do a very basic steady 1D analysis of gas flow without friction, but with heat addition, essentially Rayleigh flow. Okay. So, now before we go into this, why do we want to do this? Of course, the process that happens in a scramjet is very complex, okay? But this will tell us some very important design considerations in a scramjet engine, and phenomenologically what happens when you add heat into a supersonic flow. So, by doing a very simple analysis we will get some insights. So, that is why this analysis is important. So, this is what we want to know, that we will do a 1D analysis. Of course, you can question that that the actual flow inside a scramjet is not 1D, but still it is the gradients or the flow is predominantly in the axial direction, and we can incorporate this heat addition, even friction effects in some cases by in a simplified 1D flow. So, this will give us very important design insights we can generate by doing a 1D analysis of the gas flow without friction, but with heat addition. So, it is a basic, very basic condition that one can think of in a scramjet combustion. So, of course, the heat addition, now this can happen due to combustion, and as it happens in a scramjet engine. Okay. So, let us do this analysis. So, of course, we need the governing equations. So, the first governing equation that you need is continuity, which is the conservation of mass, and in this 1D flow you can write rho times u times a is equal to constant. Rho is the density, u is the velocity, a is the cross section area, and we can write ln of rho u a is equal to another constant, and we can write ln rho plus ln u plus ln a is equal to c, and then we can differentiate. We can write d rho by rho plus du by u plus dA by a is equal to 0. Now, here the flow through which the tube through which the flow is happening is constant. So, a, this is also a, this is also a. Okay. So, the area is not changing. So, if area is not changing, then this term goes to 0, and we can write d rho by rho plus du by u is equal to 0. Okay. Now, let us consider the momentum equation. Here, of course, if we write in the form F is equal to ma, then F is my pressure gradient. Okay. I can write dP dx, or if I just write dP is equal to minus rho u times du, mass per unit volume times the acceleration. Okay. And I can write the energy in just the form of dH0 is equal to dH plus u du. Okay. Whereas H0 is the stagnation enthalpy or total enthalpy. Now, if I go to this, if I keep this apart for now, okay, if I just go into this, and if I say that this is my constant area duct and this is my station 1, and I am interested in whatever is happening at any point. Okay. So, this is my station x essentially. So, when the flow is happening from this from the right to the left. So, 1 is my inlet station. Okay. So, if I integrate between 1 and any point, okay, so what I get is that P minus P1 is equal to minus of rho u times u minus u1. Okay. Why I can write like this? Because this quantity rho u is fixed, is equal to f. Okay. From here itself you see that rho u is equal to fixed. There is a mass flux, because the area is constant, the mass flux is essentially constant. Okay. So, I can also write P minus P1 is equal to minus rho 1 U1 times U minus U1. So, this is just an artifact of continuity, as you know. Okay. Or I can write P minus P1 is equal to rho 1 U1 squared minus rho U squared. Okay. That's right. Now, let me define a Mach number here. So, Mach number is equal to U by A. U is the flow velocity, A is the sound speed. Okay. And if ideal gas, for ideal gas, A is equal to root over gamma RT. Okay. R is the gas constant. Okay. And of course, you know P1 is equal to rho 1 or T1. So, then it implies I can write M1 square. If I multiply, I can write M1 squared is equal to U1 squared divided by A squared. Sound speed is essentially, no, I can write as essentially A1 squared. So, this is essentially U1 squared divided by gamma R T1 if I multiply both sides by rho 1 and rho 1, then I get essentially rho 1 squared by U1 squared is equal to gamma P1. Okay. So, I can have M1 squared is equal to this. Rho 1 U1 squared divided by gamma P1. This implies P minus P1 is equal to gamma P1 M1 squared, because what I am doing is that I am substituting this thing into here. Okay. And similarly, this is essentially gamma P M square. Okay. So, this implies P times 1 plus gamma M squared is equal to P1 times 1 plus gamma M1 squared. M is the Mach number at this point M. This is the inlet Mach number. P is the pressure here, P1 is the pressure here. Similarly, A1 is the sound speed here, A is the sound speed here. Okay. Now, as we will see that we will essentially consider that there is some heat addition here. So, this will be the T0 stagnation temperature here, and this will be the stagnation temperature here. So, now we can use this to write P by P1 is equal to 1 plus gamma divided by 1 plus gamma M square. Once again remember that this is my constant cross section duct, this is my inlet point which is 1, this is P1, M1, A1, T1, T01, okay, and this is P, M, A, T, T0, and this is by any point x. And of course, there is some heat addition, there can be some heat addition which essentially increases this temperature T from T01 to T0, which will come. Now let us come to temperature. Okay. So to develop temperature equation, we can once again go back to the ideal gas law. P1 is equal to rho 1 R T1 and P is equal to rho R T. Okay. So therefore, T by T1, okay, is essentially P by P1 times rho 1 by rho. Okay. Now, if you remember, rho 1 U1 is equal to rho U, okay, by continuity. So this implies rho 1 by rho is equal to U by U1. So this implies T by T1 is equal to P by P1 times U by U1. Okay. Also, now you can replace this U with Mach number, but when you bring in Mach number, there will be additional temperature that comes. So as you know, M is equal to U divided by root over gamma R T, and M1 is equal to U1 divided by root over gamma R T1. This implies U by U1 is equal to M by M1, Mach number at M, Mach number M at x divided by Mach number M at M1 at point station 1. Okay. So U by U1 is equal to M by M1 square root of T by T1. Okay. Now you can substitute this full thing to here. This gives T by T1 is equal to P by P1 times M by M1 times T by T1, and this implies T by T1 is equal to P by P1 M by M1 all square. So now I can use this relationship and put it here. This will imply T by T1 is equal to 1 plus gamma M1 squared divided by 1 plus gamma M squared. So this is the ratio of temperature at this point T divided by T1, and of course there is some heat being added Q, which essentially has increased this T by from T1 to T, but we will not explicitly consider this T or this Q, we will just consider in terms of the temperature raise and how does that relate to Mach number. So that given the Mach number is M here and given the Mach number is M1 here, how is T0 and T01 are related? That is what we would like to find. Just as you find that how is T and T1 are related, that if the Mach number is M here and the Mach number is M1 here, so then the T and T1 must be related by this manner. Of course, the T to T1, the T1 to T change has been inflicted by some external agent, which is can be heat addition or rejection, as the case may be. Okay, now to develop the relationship for stagnation temperatures, of course stagnation temperature is essentially a measure of the total energy of the flow, both the static temperature plus the kinetic energy. So which is better quantified by the stagnation enthalpy H0 is equal to H plus U square by 2 So, this is the stagnation enthalpy or total enthalpy. We should not confuse this total enthalpy with the total enthalpy when we defined as like the standard state enthalpy plus enthalpy of formation, or the sensible enthalpy plus the enthalpy of formation. This is only this enthalpy is essentially can contain both the sensible enthalpy and the enthalpy of formation. Okay. So, this is the stagnation enthalpy, which is the essentially this total enthalpy, this enthalpy plus the kinetic energy. So, this enthalpy can contain the sensible enthalpy plus the enthalpy of formation. So, that you have to remember. Okay. So, now we can of course write dA dt is equal dH is equal to Cp dt, and we can write T0 is equal to T plus U square by 2 Cp. Okay. So, then this T0 by T is equal to 1 plus U square by 2 Cpt. Okay. You can write this, and of course, if you remember Cp is equal to gamma r by gamma minus 1. So, we can put this Cp value here, and we get T0 by T is equal to 1 plus gamma minus 1 by 2 U square by S square is equal to 1 plus gamma minus 1 by 2 m square. Okay. So, this is a very standard relationship which you know from gas dynamics. So, T0 by T is equal to 1 plus gamma minus 2 by m square, gamma minus 1 by 2 times m square. Okay. Now, similarly you can also write, so this is at this point T0 by T, the ratio between these two things. We can write T01 by T1, that is a ratio between these two things, as similarly 1 plus gamma minus 1 by 2 m1 squared. Okay. So, we can write we can essentially write that T01, we will come to this plot later, do not worry about it. So, we will write that T01 divided by 1 plus gamma minus 1 by 2 m1 squared is equal to T1, okay, and T0 divided by 1 plus gamma minus 1 by 2 m squared is equal to T. Okay. So, we can write the ratio of T0 by T1, T01 by T01 by T0, okay, as essentially T1 by T times 1 plus gamma minus 1 by 2 m1 squared 1 plus gamma minus 1 by 2 m squared, and then if you invoke this relationship into this thing T1 by T, what you get is essentially, I will write down the final expression, T0 by T01 is equal to 1 plus gamma m1 squared by 1 plus gamma m squared times m by m1 whole squared times 1 plus gamma minus 1 by 2 m squared divided by 1 plus gamma minus 1 by 2 m1 squared. Okay. Now, this 1 is not a standard state, it can change. So, we can just write that if we can replace this with it can be any state, right. So, to maintain a standard reference state, we can say that this m1 is equal to 1 and this T01 is equal to T star, T0 star. So, we can write that T0 by T0 star, which refers to Mach 1 condition, is essentially, if you put m1 equal to 1, what you get is essentially this following, is 2 times gamma plus 1 m squared times 1 plus gamma minus 1 by 2 m squared divided by 1 plus gamma m squared whole squared. Okay. So, the star signify properties at m equal to 1. And then if you plot all these things, we can also generate relationships where P0 by P0 star, T by T star, and T0 by T0 star. And if we plot all these things here as a function of this Mach number in this log plot, log plot Mach number, and these are like different ratios you see, this tells you a very, very interesting thing. Okay. Let us consider this plot. This T0 by T0 star plot, which is essentially a solution of this. Okay. This if you plot this, you will get this. Okay. So, if you plot this, okay, what do you get? So, suppose you are at a Mach number of 3, okay. Your T0, your m is equal to 3. So, that will tell your T0 by T0 star is given by about, what is this value? This is about say 0.65. Okay. Now, due to heat addition, your T0 will increase. Okay. So, T0 goes up. So, but all points to whatever T0 must fall on this line. Okay. So, if the T0 goes up, what happens? So, then if the T0 goes up, you have to basically, you see, are moving, T0 increases towards the left. So, you have to move in this direction. Okay. So, as you are moving in this direction, okay, what happens? You see your Mach number is dropping. So, you see as T0 goes up, okay, your m is reducing, okay, and it can reduce, okay, you can show that for the T0 to continuously go up, it can only go up to this point, okay, it cannot go up any further, and this point, which is the maximum of T0 by T0 star, is given by m equal to 1, okay, which is of course obvious, because star corresponds to the conditions where Mach equal to 1. So, you see that by heat addition, the immediate consequence is that of heat addition is that your stagnation enthalpy goes up H0, which means your stagnation temperature goes up. So, if your stagnation temperature at a Mach 3 flow, suppose this is your combustor entry condition at Mach 3. So, if you are adding heat which raises T0, it immediately progresses in this direction, and you see it can only, you can add heat only up to this point where your Mach number is equal to 1, okay, because you cannot add more heat, because after that you see this line drops. So, you can only add heat up to the Mach number 1, and that is the point beyond which you cannot add any more heat, and that is where the flow is choked, and that is corresponds to the sonic conditions m equal to 1. So, this is called thermal choking, that is choking by heat addition. So, similar thing happens for here also, that if you have a Mach number of say 0.3 and you are adding heat, so you see you go towards the sonic conditions, okay. But the thing is that here with the addition of a small amount of heat, you can reduce your Mach number drastically. So, that is the point, because the slope is much smaller here. Here you need to add a lot of heat to go to Mach equal to 1, but in this side you have to have a little bit of it to even go to Mach number 1. So, this is the consequence. Why does this happen? This is the consequence of the fact that our area is constant, okay. So, this constant area can only support a limited amount of heat addition or a limited amount of stagnation temperature rise, okay. Beyond that, the flow gets choked, and this is thermally choked, and you reach a Mach number 1, which is of course not wanted in a scramjet. So, what do you do? In a scramjet, what you do is that in the combustor you provide a little bit of divergence, okay. That is, you increase the cross sectional area to prevent this thermal choking. So, now you see, if you go back into these things, into all these designs, you see this is a little bit diverging in comparison to this. This, even if it is schematic, is diverging in comparison to this, Okay. So, that is the reason to prevent thermal choking you provide a small amount of divergence into this scramjet combustor, and that emerges out. The reason for this, why should divergence should happen, immediately comes out of from this Rayleigh flow analysis. Okay. So, this is the whole idea that you should have in a scramjet you should have you should provide a small amount of divergence, and then basically there is something called pressure area tailoring that one needs to incorporate. That is, how do you want the pressure to change in your combustor, and that's a little bit involved topic, and then we'll go into to take those up. We'll go into essentially the different aspects of some very basic aspects of scramjet combustor design. Basically, the way how to do it instead of actually providing the design methodology here, because this course is about more fundamentals of the processes that happens in the scramjet engine rather than the designing the scramjet engine itself. But I hope this Rayleigh flow analysis, that is this frictionless flow with height addition, that is frictionless flow in which the stagnation temperature is increasing. This kind of a flow, this kind of an analysis tells you that why you can only add increase the stagnation temperature up to a certain limit before thermal choking happens, and to avoid thermal choking you need to provide some divergence into the scramjet combustor. So, in the next class we will go into the design considerations and basics, and then we will go into the different phenomena that happens in a scramjet combustor. So, till then, thank you.